Hello friends, this video on DNF block elements part 27 is brought to you by examfear.com. No more fear from exam. The first is what is meant by disproportionation of the oxidation state. Give an example. See the reaction where my reduction and oxidation take place simultaneously, it is called disproportionation. For example, Cu2O, if you react with sulfuric acid, it forms copper sulfate, copper and water. So if you see, the copper has oxidation to +1, here +2 and here 0. So +1 to 0 and +1 to +2. Both this is happening in this reaction. So this is called disproportionation reaction. The next is why Cu plus is not stable in aqueous solution. Cu plus. If you talk about the oxidator Cu plus, it is argon 3D10 4s0. So typically it has to be stable because d orbital is full, but actually it is not, because copper plus iron oxidize and reduce simultaneously in the aqueous solution. Please note there is a catch called aqueous solution to form copper plus ions and copper. We'll show you the reaction. Cu2O plus, give me sulfuric acid, reacts and it forms CuSO4 and copper and water. The same reaction. It was +1, it becomes +2 and 0. So it's oxidized and reduced simultaneously, right? So you can write that Cu plus gives Cu2 plus and Cu. So because of this is solid, this is aqueous, and this is also aqueous. And because of this, Cu plus is not stable. You write the electronic configuration of Cu3 plus, Cr3 plus, Cu plus, Cu2 plus, Mn2 plus. Let's write the electronic configuration of Cr3 plus. Cr is chromium. Chromium 3 plus electronic configuration will be Ar 3D3 4s. Why? See, chromium electronic configuration is Ar 3D 5 4s1. From this you plug out 2 electrons. First electron will go from s, the second electron will go from 3d orbital, and the third electron will again go from 3d orbital. So the electronic configuration will be Ar 3D3 4s0. The next is Cu plus. For copper electronic configuration, we have seen that is argon 3D10 4s1. So if you make Cu plus, you take out one electron, this electron will come out. So the electronic configuration will be Ar 3D10. Let's talk about cobalt. Cobalt, the electronic configuration, we know that 3D7 4s2. Okay, from this you want to make cobalt 2 plus, 2 electrons will come out of 4s orbital. The cobalt 2 plus will look something like this. Ar 3D7 4s0. Similarly, manganese, the electronic configuration is argon 3D5 4s2. So take out 2 electrons, it will come from here. There is 4s orbital. The Mn2 plus electronic configuration will be Ar 3D5. Okay. Write down the electronic configuration. We have more electronic configurations to write. Actually, I'll just write the values. You can try on your own. PM3 plus, it is xenon 4f5. Cerium 4 plus, it is xenon 4f0. Lu2 plus, it will be xenon 4f14 5d1. TH4 plus will be RH 5f0. Actually, you can try this. You can write the full electronic configuration of these metals and then remove the electrons to get this electronic configuration. The question is why Mn2 plus are more stable than Fe2 plus towards their oxidation +3 states. See, it says that Mn2 plus to Mn3 plus is difficult, but Fe2 plus to Fe3 plus is easy. Why? Let's see the electronic configuration. Mn2 plus, it is argon, and then it has 3d5. Mn3 plus is argon, 3d4. Let's talk about iron. Fe2 plus is argon, 3d6, and Fe3 plus is argon, 3d5. Now if you see, Fe3 plus is stable, 3d5. So, but Fe2 plus is not that stable, it is 3d6. So Fe2 plus will have tendency to become Fe3 plus because it will attain extra stability. If we talk about Mn2 plus, it is stable, 3d4. Mn3 plus actually is not stable because it is 3d4. So this is not stable, so it will not have tendency to form Mn3 plus. It's all about stability. So most of your answers will be in the electronic configurations. Explain briefly how +2 oxidation state becomes more and more stable in the first half of the first row of the transition metal with increasing atomic number. So first half of the first row, that is these elements. And here we have to see what is the trend for +2 oxidation state. If you see, for scandium, it is +3, that is the most prominent oxidation state. For titanium, it's +4, vanadium is +5, chromium +6. Only for manganese, +2 oxidation state is the most observed state or most stable state. Why? If you see the electronic configuration, scandium is what? 3d1, 4s2. Let me write for all. Titanium is 3d2, 4s2. Then we have vanadium, 3d3, 4s2. Then we have chromium, 3d5, 4s1. And then we have manganese, 3d5, 4s2. Okay. Now, if you lose 2 electrons from here, 4s2. If you lose 2 electrons from here, Sc, this becomes, this is all for Sc, one normal state. Scandium, let's find +2 oxidation state. This becomes 3d1, 4s0. Titanium, +2 oxidation state, 3d2, 4s0. Vanadium, +2 oxidation state, 3d3, 4s0. Chromium, oxidation state of +2 is nothing but 3d4, 4s0. And manganese, +2 oxidation state is 3d5, 4s0. So if you see in all these, none of these is stable, only this is stable. Only Mn2 plus is stable. Why? 3d1, 4s0, no stable configuration. 3d2, 4s0, no stable configuration. 3d3, 4s0, no stable configuration. In fact, none of these are stable. Thus, as far as +2 oxidation state is concerned, only Mn2 plus is stable. Okay. To what extent the electronic configuration decides the stability of oxidation state in the first series of the transition metal? We are talking about the first series. This is the first series, and the question is, to what extent the electronic configuration decides the stability? See, for scandium, the +3 is the oxidation state, stable. So we talk about Sc +3. If you see, the electronic configuration is 3d0, 4s0. This is the stable configuration. Talk about titanium +4. The electronic configuration is again 3d0, 4s0. Talk about vanadium +5. The oxidation state is again 3d0, 4s0. Right? You have argon here, definitely in all. Same thing you talk about chromium. So vanadium is done. Chromium has +3 and chromium has +6. So chromium +6 is again this one, 4s0. Let's talk about chromium +3. It will be argon, 3d3, 4s0. This is again T2G configuration, stable, and this is again all stable, okay, because there are 0 electrons in the orbital. So this is also, these are all governed by electronic configuration. Mn2 plus, let's see. Mn2 plus. Mn2 plus electronic configuration will be AR 3d5 4s0. This is also correct. This is stable, half filled. Mn7 plus will be argon 3d0 4s0. This is also correct, all empty, so all filled actually, so this is also correct. Fe2 plus first, let's find Fe2 plus will be what? 3d6 4s0, and Fe3 plus is argon 3d5 4s. So based on electronic configuration, Fe3 plus is stable, but Fe2 plus is not that stable. Correct? But this still exists. This is the one example where the electronic configuration is not driving the stability of the oxidation state. Talk about cobalt now. We'll talk about cobalt. Cobalt 2 plus, it will be 3d7 4s0, right? And cobalt 3 plus will be 3d6 4s0. In fact, cobalt plus 4 will be 3d5 4s0, which is stable electronic configuration, but that is not stable. Stable is cobalt plus 2 and plus 3. In fact, these are also not governed by electronic configuration. Okay, if we talk about nickel now, nickel plus 2. Nickel plus 2 will be what? 3d8 4s2. Still, this also doesn't have any stable electronic configuration, but it is stable. Copper plus 2. Copper plus 1 actually, if you see, has stable electronic configuration, but that is not the stable oxidation state. Copper plus 1 oxidation state, electronic configuration will be 3d10 4s0. But this is not stable. Copper plus 2 is stable, which has electronic configuration of 3d9 4s0. So up till this part, yes, electronic configuration governs the stability of oxidation state, but iron plus 2, cobalt plus 2, cobalt plus 3, nickel plus 2, in fact copper plus 2, these doesn't follow. In fact, zinc plus 2 follows. Zinc plus 2, if you see the electronic configuration, it will be 3d10 4s0. It follows. So these ones with the square box, they don't follow. 5 oxidation states: iron plus 2, cobalt plus 2 plus 3, nickel plus 2, and copper plus 2. These are stable oxidation state, but as per electronic configurations, they are not. So there are different factors which actually make them stable. The question. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.